lecture we are going to talk about top down design methodology in digital voltage mode control, particularly using hardware descriptive language. So, here we will talk about digital voltage mode control architecture, then we need to identify what are the real circuit scaling factors, gains, then we need to identify overall design requirement and some overview of top down design methodology. So, in this particular architecture we are talking about digital voltage mode control, and this we have discussed multiple time in week 2 as well as week 3 in the MATLAB implementation, where we need an A to D converters for the output voltage we are sampling and then everything else in digital domain. So, that means the data coming out of the digital that is coming, then all the reference signal, sawtooth waveform, everything we are generating inside the digital platform. So, here for practical constraint we need to understand that how is it linked. First of all, when you take a practical converter, for example, if we emphasize this part, so there is a first of all the scaling feedback gain, because we need to provide this voltage to the ADC input, which must be consistent with the ADC span, including the overshoot, undershoot, the startup behavior of the converter. So, the output voltage after scaling down, that should not go out of the range of the ADC, that we have to, that means that is one way the safety purpose. Another is the mapping between the number, the voltage must be within the span of the ADC, and that is why you need to select suitable R1 R2 ratio. And in this particular design we are going to show hardware also in the subsequent lecture. We have considered this scaling factor to be 0.27, which is, that means I would say this voltage feedback, which is the feedback voltage, is some feedback gain by this output voltage, where feedback gain is approximately equal to 0.27, because by virtue of the resistive divider we are getting like this. Now, that means if we consider this particular architecture and we are talking about, now we want to develop, what do we want to develop? We want to develop, because this digital platform we are using an FPGA, that means field programmable gate array device. This FPGA only can take digital data and it can only give rise to digital data, that means it has IO pin which only accept digital data in and out. So, this is the digital control where you are using FPGA. What is coming to the input to the FPGA or the digital controller? The data coming out of the ADC, and that we are talking about ADC data. And here we are talking about at ADC, we have discussed in the previous lecture when we talk about the signal conditioning circuit. Here we are using an ADC which is a differential ADC, fully differential ADC, 10 bit ADC, 10 bit. This ADC requires a clock because we need to provide sampling, and we are using a pipeline ADC from analog device. So, it is a pipeline ADC. In pipeline ADC, actually the processing, that means the propagation delay or basically the sampling or the conversion time depends on the number of clock cycle. Instead of absolute value of the conversion time is a number of clock cycle, and in this case there are 6 clock cycle. That means the throughput is the same as like flash ADC, but it has a latency of. So, what is the latency? That means the delay, that is the sending the sample comment and the data ready, that takes around 6 cycles. Okay. So, now since it takes 6 cycle, we have to be very careful about the frequency of the ADC, because if we give a lower frequency it will take 6 cycles. So, the total delay of the conversion will be pretty large, and that will actually create a lot of problem in your control loop. First of all, the transient response all. So, we need to provide sufficiently high frequency clock, so that with 6 cycle your delay will not be too large. So, in our case we are using FADC to be 25 megahertz, but another practical aspect, because it requires 5-6 cycle to get the data ready from the start of the conversion to the end of the conversion. But after this 6 cycle we may not want to continue this sampling of the ADC, because we do not need the output voltage, we need again the next. For example, we have this switching frequency clock. Let us say this is my switching frequency clock, and we need to sample the ADC, let us say just before it starts. That means, we are giving a high frequency clock of this kind of clock 6 data. So, data will be kind of ready here. So, as if the data was captured like here, but we may or may not continue this clock. This is my F ADC. If we continue, then ADC is unnecessarily burning power when you do not need data. So, we have to be only careful, the 6 cycles are needed, which will be end close to that switching point. So, the data should be ready. That means, that is the first requirement. So, after that you can do some kind of windowing operation, where the ADC clock will be forced to 0. That means, there is no ADC clock going on, there is no activity, there is no sampling, and you again start doing something somewhere here, because you need another 6 cycle data to the data to be ready, again you turn like that way. But for simplicity in this experiment, we are continuing 25 megahertz to the ADC continuously, but in real implementation we can minimize the power consumption by this. So, the ADC data is 10-bit data, is a 10-bit sine data, the sine data. Now, here the transient, that means, we are also making a transient. That means, for load here, that means, if we take the output capacitor, we are using a continuous load and we are also using a transient load. So, this we get signal, we are talking about Q load, and that is the output. That means, if this is high, then this resistance, so this is your continuous resistance, this is another resistance like R dash, they will come in parallel. So, the effective resistance will be down smaller. So, as if it will look like a step up transient. So, net current will increase. So, it is a step up transient, and this PWM high and PWM low are going to the gate drive circuit, and there will be a gate drive circuit, gate drive. So, the gate drive will generate actual gate signal for the MOSFET, but we are providing high and low of this gate drive signal from the FPGA. Some IC gate drive circuit also has, it only accept only one PWM signal, and internally it generates the dead time, all other signal, so that it can be adapted to dead time. But in this particular driver we are using, where we are dedicatedly giving low side and high side gate signal, and the driver circuit makes it compatible for this MOSFET to turn on and off. So, that means, this high side and low side are the gate signal, and in between there should be some dead time. This tran, Q tran we are giving, it is to select whether we want to make a load transient or whether we want to make a reference transient. So, that is also added. Now, so that means, FPGA input to the FPGA is the ADC data, input to the FPGA is the transient type that we detect, and the clock of the digital controller, and this we are taking 100 megahertz, 100 megahertz, and that will be a crystal oscillator outside. Output of the FPGA, one is the ADC clock signal, one is the high side and low side gate signal going to the gate drive circuit, another is the load transient command, whether you want to turn on this switch or not. That means, it is linked with this. Okay. So, now we want to design this particular thing, and how does it look like? So, again I discuss this K actual output voltage, you have a resistive divider, and this gain we are taking around 0.27. After that scaled, it is coming to the input to the ADC, and now the ADC data is going out, and we have discussed this ADC data is ADC data. Inside we are assigning, because this data is coming at a higher rate, because we are using a 25 megahertz clock. So, continuously this data is coming at the rate of 25 megahertz, because the throughput of the ADC is 25 megahertz, but the latency is 6 cycle clock cycle. That means, our samples are available of all this ADC, if this is my F ADC. But let us say we want to capture this sample somewhere this point, because this is continuous, though this is my F switching frequency. So, we are calling the data which is captured right here, that means there will be output voltage. So, as if these samples were captured here and this sample is available here, that means this to this we are assuming 6 cycle latency. So, this data actually will be captured here and this is n out, that means the inside what is the output voltage number corresponding to the output voltage is nothing but a sample voltage which was sample 6 ADC cycle earlier. That means there is a sample first and then you switch. Then this is available and this is captured, that means we need a clock synchronized data access and that will n out and will go to the Verilog code. Now, once it is captured, that is the number, because we have discussed the Q format and this is in the format of Q1.9 sine format. So, we need to provide the n rep accordingly, because there is a scaling factor, so that it is acting like a reference V reference voltage in the digital command, that is why it is n rep. And then the n error, it is going to the controller. So, we are using a PID digital PID controller and that controller output is going and there is a sawtooth waveform and then this is a trailing edge modulator, and after this modulator we will have a dead time circuit to generate Q high and Q low. So, eventually this whole block is actually shown in this red line. That means we need to design, this is a practical implementation. So, this circuit, if we take from the feedback to the gate signal, it will look like this, okay, that we have discussed. Now, top down design methodology. So, we want to design this, we call it as a digital underscore voltage mode control, because we want to make a Verilog module. We have already discussed Verilog in detail. So, we want to create a module which is the main module, and that name is digital VFC. Main module will interface with the external world, and the first is the ADC data. Second, it is going out the a clock signal, clock coming in, the PWM going out, and there will be one more which will be Q load, and there will be one more input which will be Q transient type. So, this interface is taking place inside this controller. So, the external world, it is dealing with all digital number, either gate signal or ADC data or clock, but it is only dealing with 0 and 1. It can be scalar data or vector data. So, we need to design this main module, we need to subdivide into multiple parts. So, the top down, our digital voltage mode control, which will interface with the external world, this is my main module. So, as if I am designing a digital IC, you can imagine, because FPGA is emulating like an IC, which interface with the world with digital data from ADC, sending gate signals and so on. But this module inside, if you go inside, there will be multiple blocks. The one block will be clock generation, because we need to generate switching frequency clock, we need to generate ADC clock, here we do not need a DSC clock. So, this clock generation will generate this clock. The second one, it require digital PID controller, because this controller is nothing but this. Okay. So, this will generate PID, then other one will be digital DPWM. So, it is a, I would say, counter based DPWM. So, it is a counter based DPWM plus dead time. So, these are included because we are talking about this entire block, this include all this entire block. So, there are multiple such sub module which will make the full overall module. Okay. So, I am going to discuss the more detail about the Verilog coding in the subsequent lecture, but in summary we have one module which you know that in the main module we can instantiate other module. So, I have not shown the main module yet, I will come to that part in the subsequent lecture, but the main module we are instantiating another module which is a clock generator I just told. We are instantiating another is the digital PID controller, and we are instantiating another which is a DPWM plus date time. So, these are the 3 sub module, and on top of that there is a main module. So, in summary we have discussed digital voltage mode control architecture, we have we try to identify what are the real scaling factors and gains, then we talk about overall design requirement and just an overview of the top down design methodology. That is it for today. Thank you very much.